Okay, welcome to this session. Now we will be continuing whatever the example we were talking about in the last lecture. We have just we have taken up one example of set of non-homogeneous algebraic equation for the solution using the eigenvalue eigenvector method. So we took up a 2 dimensional problem, 2 into 2 matrix for demonstration purpose. The whole procedure can simply be extended for a higher dimensional problem numerically, that we have already discussed in the last class. Now, let us come back to the specific example that we are talking about. So, in this example it is a two dimensional problem. So, we followed the various steps to be adopted to solve this problem. The first step, one has to get the evaluation of eigenvalues. So, we have identified we have evaluated the eigenvalues for the matrix A in this particular case, and these eigenvalues turned out to be -4 and -1. Next step is to evaluate the eigenvectors of the corresponding eigenvalues, and we have already evaluated the eigenvectors for this matrix A, x1 and x2. Next step is evaluation of eigenvalues, eigenvectors vectors A transpose. We have already proved the eigenvalues will be the same for A and A transpose, that we have already proved earlier. So, this is step number 2. So, evaluation of eigenvectors of A transpose. So, eigenvalues for this A transpose are identical. A transpose are same as -4 and -1. So, for lambda 1 is equal to -4, let us evaluate the eigenvectors of this A transpose matrix. So, -2 minus lambda 1 1, 2 minus 3 minus lambda 1, x 1 x 2 are the elements of this vector is equal to 0. So, if we put as lambda 1 is equal to -4, you will be getting 2 1 2 1 x 1 x 2 equal to 0. So, you will be getting 2 x 1 plus x 2 is equal to 0 from this, and 2 x 1 plus x 2 is equal to 0. So, they are identical. So, if you select x 1 is equal to 1, then x 2 has to be -2. So, therefore, y 1 is equal is 1 minus 2 is an eigenvector for the eigenvalue lambda 1 is equal to -4. So, in case of lambda 2 is equal to -1, you will be having -1 1 2 minus 2. I am just writing from this equation, I am just writing this one. So, I am just omitted one step here. They are identical. By now, it has to be clear to you, and you also know how to evaluate eigenvalues of eigenvectors given a matrix. So, this will be minus x 1 plus x 2 is equal to 0, and 2 x 1 minus 2 x 2 is equal to 0. They are identical. So, if you select x 1 is equal to 1, then x 2 turns out to be 1. So, therefore, y 2 is equal to 1 1 is an eigenvector to eigenvalue lambda 1 is equal to -1. So, therefore, this the same method, the same way we have evaluated the eigenvectors of matrix A, we can evaluate the eigenvectors of matrix A transpose. Now, let us write down these the solutions in one place. So, we have the eigenvectors x 1 is 1 minus 1 and x 2 is 2 1, okay, and y 1 is 1 minus 2 and y 2 is 1 1. So, this corresponds to lambda 1 is equal to minus 4, these 2 corresponds to lambda 1 is equal to minus 1. So, they are eigenvectors of A and they are eigenvectors of A transpose. So, and eigenvalues you know, lambda 1 is equal to minus 4 and lambda 2 is equal to minus 1. Okay. Next step, that is step 3. We have already finished step 1 and step 2, that is the evaluation of eigenvectors of A and evaluation of eigenvectors of A transpose. So, next step is to get the solution of B is equal to summation beta I x I, and this in this case I is going to 1 to 2. So, beta 1, if you remember, beta 1 is nothing but y 1 transpose B divided by y 1 transpose x 1. So, if we write it down, it becomes y 1 transpose. So, it will be 1 minus 2. So, this will be simply 1 minus 2, the rows becomes the column becomes rows. So, it becomes 1 minus 2, rows becomes columns, okay. And B is minus 1 0 and y 1 transpose is same as 1 minus 2 and x 1 is 1 minus 1. So, if you compute this is 1 into minus 1 plus minus 2 into 0, that is 0, divided by 1 into 1 plus minus 2 into minus 1. So, this will be plus 2. So, it will be minus 1/3. So, beta 1 is minus 1/3. Similarly, we calculate beta 2. Beta 2 will be y 2 transpose B divided by y 2 transpose x 2, and y 2 transpose will be 1 1 minus 1 0 1 1 and x 2 will be 2 1, x 2 will be 2 1, and we get this will be minus 1 plus 0 into 1, that will be 0, 2 into 1 plus 1 into 1. So, this will be minus 1 upon 3. Okay. Next, we evaluate alpha 1 and alpha 2. If you remember that alpha I was equal to beta I by lambda I. So, once you get the betas, then you will be able to, and you know already know the lambdas. So, you can get the alpha i's. So, alpha 1 will be nothing but beta 1 by lambda 1. So, beta 1 will be minus 1 upon 3 and lambda 1 is minus 4. So, this will be plus 1 by 12, and alpha 2 is minus 1 upon 3 divided by minus 1. So, this will be plus 1 upon 3. So, now since the alphas are known and xi's the vectors, the eigenvectors of A are already determined, you will be in a position to get the solution matrix. So, the solution matrix is, or solution vector is given as, vector is nothing but a special matrix. So, solution vector is given as x is equal to summation alpha I x I. So, you will be having two elements of the solution vector x 1 and x 2. So, this will be alpha 1 x 1 plus alpha 2 x 2. Alpha 1 is 1 by 12 and x 1 we have already found out 1 minus 1 plus alpha 2 is 1 upon 3. So, this will be 2 into 1, 2 and 1. So, this will be equal to, so we will be getting the solution matrix, solution of this problem, solution elements x 1 is equal to 1 by 12 into 1 plus 1 by 3 into 2. So, it will be 2 by 3. So, therefore, 12, 1, 8. So, this will be 9 by 12. So, it will be 3 by 4. Similarly, the other solution is 1 by 12 with a minus sign plus 1 upon 3. So, this will be 1 upon 4. So, 3 by 4 and 1 over 4 is the solution of this particular problem. So, the solution vector x will be comprised of two elements 3 by 4 and 1 by 4, and that gives the complete solution to this problem. So, that is how this problem clearly demonstrates the solution using the eigenvalue problem, how to get the solution using the eigenvalue and eigenvector method without doing the without taking recourse to the matrix inversion that is necessary for utilizing Gauss-Seidel algorithm or Gauss elimination method. So, we will be taking up one more example in the in this type of problem, simply because the eigenvalues in that particular problem becomes imaginary. It becomes imaginary. So, you need not to worry about that. Depending on the situation, depending on the definition of the problem, one can get real valued eigenvalues or imaginary eigenvalues, but the final solution will be a real solution if it is a real valued problem, because all chemical engineering systems are real valued problem. So, finally, you will be getting a real solution even if the eigenvalues are imaginary. That is the reason I will be taking up this particular example, where the eigenvalues you will be getting as imaginary. So, the next problem is example 2, and we are going to solve this equation non-homogeneous set of algebraic equation A x is equal to b, where the matrix A is 1, 2, minus 2, 1, and the vector b is 3 and 4. So, let us look into the solution. Step number 1 is eigenvalues of A. That is nothing but determinant of A minus lambda I is equal to 0. So, we compute that 1 minus lambda 2 minus 2 1 minus lambda, that will be equal to 0. Open up this determinant. If you open up this determinant, this becomes 1 minus lambda square plus 4 is equal to 0. So, you will be getting lambda square minus 2 lambda plus 5 is equal to 0. So, lambda, so it is a quadratic, the two solutions correspond to the two eigenvalues. So, lambda 1 2 will be minus b. So, it will be plus 2 plus minus under root b square 4 minus 4 a c. So, 20 divided by 2. So, it will be 2 plus minus 4 I divided by 2. So, you will be having imaginary eigenvalues in this particular problem. So, lambda 1 becomes 1 plus 2 I, and lambda 2 is equal to 1 minus 2 I, and these roots they occur as complex conjugate. Okay. So, let us talk about the first root, and we will be evaluating the corresponding eigenvectors. So, corresponding to eigenvalues, next we evaluate the eigenvectors of the matrix A. So, for eigenvalue lambda 1 is equal to 1 plus 2 I, we will be having A minus lambda 1 I, lambda 1 I, x 1 is equal to 0. So, x 1 is the eigenvector corresponding to eigenvalue lambda 1. So, therefore, we will be getting this as 1 minus lambda 1 2 minus 2 1 minus lambda 1, x 1 x 2, these are the elements of the eigenvector x 1. So, you put the value of lambda 1 as 1 plus 2 I. So, this becomes minus 2 I to minus 2 plus and 1 minus lambda 1, again it is minus 2 I. So, to this, so you formulate the two equations. So, minus 2 I x 1 plus 2 x 2 is equal to 0, minus 2 x 1 minus 2 I x 2 is equal to 0. These two equations are identical, because if we multiply these equation by I, what you will be getting is that minus 2 I x 1, I square is minus 1. So, minus minus plus 2 x 2 is equal to 0. So, these two equations are identical, and therefore, if we select x 1 is equal to 1, then x 2 will be I. So, therefore, x 1 is 1 I is the eigenvector corresponding to eigenvalue lambda 1 is equal to 1 plus 2 I. So, x 1 is the eigenvector 1 plus 2 I is the corresponding eigenvalue. So, next we compute the eigenvector corresponding to the eigenvalue lambda 2. So, for lambda 2 is equal to 1 minus 2 I, again we get the corresponding eigenvector by solving this equation a minus lambda 2 I multiplied by x 2 is equal to 0, where x 2 is the corresponding eigenvector. So, therefore, this becomes 1 minus lambda 2 2 minus 2 1 minus lambda 2, and x 2 will be having two elements x 1 and x 2, that will be equal to 0. So, therefore, if we put lambda 2 as 1 minus 2 I here, so you will be getting 2 I 2 minus 2 plus 2 I, and x 1 x 2 is equal to 0. So, the first equation will be getting 2 I x 1 plus 2 x 2 is equal to 0, and minus 2 x 1 plus 2 I x 2 is equal to 0. Again both are identical, because you multiply this equation by I, you will be getting back the other one. So, you will be getting finally I x 1 plus x 2 is equal to 0. So, therefore, if we select x 1 is equal to 1, then x 2 will be is equal to minus I. So, if x 1 is equal to 1, then x 2 will be minus I. So, therefore, x 2 is equal to 1 minus I is the eigenvector corresponding to lambda 2 is equal to 1 minus 2 I. So, we evaluated the eigenvectors for the corresponding eigenvalues. Next step is to evaluate the eigenvectors for A transpose. So, that is step 2. eigenvectors of A transpose. So, if you look into the A transpose, this is a transpose matrix 1 2 minus 2 and 1. So, lambda 1 and lambda 2 remain the same, because we already proved the eigenvalues of A and eigenvalue of A transpose are identical. So, they remain same, only the transpose matrix elements will be changed, interchanged, rows becomes columns. Lambda 2 becomes 1 minus 2 I, they are identical. So, therefore, for lambda 1 is equal to 1 plus 2 I, we have A transpose minus lambda 1 I y 1. So, y 1 is the corresponding eigenvector of A transpose for the eigenvalue 1 plus lambda I. So, 1 plus 2 lambda I, 1 plus 2 I. So, therefore, it becomes, you just put the values here. So, it becomes 1 minus lambda 1 A transpose, or 1 minus lambda 1 minus 2, then 2 minus 2 and 1 minus lambda 1. Y 1, y 2 are the elements of the eigenvector y 1. So, therefore, minus 2 I minus 2, 2 minus 2 I y 1 y 2 equal to 0. Now, if we construct the equations, these equations becomes y 1 is equal to I y 2. So, therefore, if we select y 1 is equal to 1, then y 2 has to be is equal to minus I. So, 1 minus I is the first eigenvector for lambda 1 is equal to 1 plus 2 I. Similarly, one can evaluate the corresponding eigenvectors for lambda 2. So, y 1 is equal to 1 minus I for lambda 1 is equal to 1 plus 2 I. Next, we evaluate the eigenvector for next lambda values, the eigenvalue 1 minus 2 I. We formulate the same thing, A transpose minus lambda 2 I multiplied by y 2 should be equal to 0. So, this becomes 1 minus lambda 2 minus 2, 2 1 minus lambda 2 y 2 will be having the elements, let us say y 1 y 2 is equal to 0. So, it becomes, put the value of lambda there, lambda 2, it becomes 2 I minus 2, 2 plus 2 I y 1 y 2 will be equal to 0. So, you will be having two identical equation, and this equation in this case will be y 1 is equal to minus I y 2. So, therefore, if we select y 1 is equal to 1, then y 2 is equal to y 2 will be plus I. So, 1 plus I y 2 is equal to 1 and I is eigenvector for lambda 2 is equal to 1 minus 2 I. So, therefore, we have evaluated the eigenvectors for A, we have evaluated the eigenvectors of A transpose. Next step is step 3. For step 3, we evaluate the coefficients beta in the equation B is equal to summation beta I x I. So, if you remember, beta 1 is equal to y 1 transpose B divided by y 1 transpose x 1. So, this becomes 1 minus I and B is nothing but 3 4 1 minus I, and x 1 is nothing but 1 I. So, you will be having 3 minus 4 I divided by 1 plus I square is minus plus 1. So, it becomes 1 by 2 3 minus 4 I. So, that is beta 1. Similarly, we can evaluate beta 2. Beta 2 is y 2 transpose B divided by y 2 transpose x 2. So, therefore, this becomes 1 I 3 4 and it is 1 I 1 minus I. So, therefore, you will be getting 3 minus plus 3 plus 4 I divided by 1 minus I square. So, minus plus 1. So, this becomes half 3 plus 4 I. So, you will be getting alpha 1 as beta 1 by lambda 1. So, alpha 1 becomes 3 minus 4 I divided by 2 and lambda 1 becomes 1 plus 2 I. So, lambda 1 just put the value of lambda 1 there, and similarly we can get alpha 2 as beta 2 by lambda 2, and this becomes 1 by 2 3 plus 4 I divided by 1 minus 2 I. So, next, so we have evaluated the betas, we have evaluated the alphas. So, next and final step is the solution. X is equal to summation alpha I x I. So, the solution this becomes a solution vector already determined. The eigenvectors already evaluated. So, we just put the solution vector, these are the elements of the solution vector x 1 and x 2. So, we just open up this summation runs from index 1 to 2. So, 3 minus 4 I divided by 2 into 1 plus 2 I, that is the alpha 1. Next is x 1 is 1 and I plus 3 plus 4 I divided by 2 into 1 minus 2 I, that is the alpha 2, and x 2 is 1 minus I. So, you will be getting, just simplify the whole thing, just make it, so you just multiply both side, multiply both numerator and denominator by complex conjugate of 1 plus 2 I. So, multiply by 1 minus 2 I on top and the bottom. So, it becomes 3 minus 4 I multiplied by 1 minus 2 I divided by 2 into 1 minus plus 4 1 and I plus 3 plus 4 I 1 plus 2 I divided by 2 1 plus 4 1 minus I. So, this becomes, just keep on simplifying, this becomes minus 1 minus 2 I just omitted one more step, divided by 2 1 and I. Next we will be getting minus 1 plus 2 I divided by 2 1 minus I. So, x 1 will be getting as minus 1 minus 2 I divided by 2 multiplied by 1 plus minus 1 plus 2 I divided by 2 multiplied by 1, and if you simplify this whole thing, this becomes minus 1. So, you will be getting a real valued solution. Similarly, the x 2 will be I by 2 minus 1 minus 2 I plus minus I by 2 minus 1 plus 2 I. So, this will become 2. So, minus 1 and 2 is the solution vector for this particular problem, and if you see that although the eigenvalues are not real, they are imaginary, but the solution is a real solution. So, this example demonstrates that even the eigenvalues become imaginary, one will get a real valued solution for this particular problem. So, this gives a demonstration of how the eigenvalues and eigenvector methods can be implemented to solve the set of algebraic equations which are typically occurring for the steady state problem in any chemical engineering application, and how one will get an elegant solution using the eigenvalue and eigenvector method. Next, I will talk about solution of. So, we have looked into the solution of set of algebraic equation. So, next I will be talking about solution of set of ordinary differential equation. Solution to set of ODEs. Typically, these will be occurring, ODEs will be occurring if we will be talking about a transient problem. If we have a transient problem, then these are the ordinary differential equations may be the governing equations of the chemical engineering process. So, if there is a set of ODEs, they can be written in a compact matrix notation. One can use a compact matrix notation to detect this, to write it down. Dx dt is equal to A x. In this case, x is a vector and A is a matrix, and the initial conditions are given. This is vector at t is equal to 0 is x I. So, that will be the initial condition specified for this set of governing equation which are in the form of ordinary differential equation. Now, in order to utilize the eigenvalue eigenvector method, we have to assume the solution form as x is z e to the power lambda t. So, just lambda is a scalar, z is a constant vector, and lambda being scalar, t is the time. So, therefore, we just assume the set we just assume the solution in this form. Now, what we do next, we substitute this into this equation and see what we get. So, if we do that, we will be getting dx dt. So, z lambda z e to the power lambda t should be is equal to A x. So, lambda a. So, what A x is? A x is nothing but lambda x, because x is nothing but z e to the power lambda t. So, if lambda is this scalar given in this form, you will be finally getting x is equal to lambda x. So, now I think we will be able to get the identify the form of this equation this is a standard eigenvalue problem. So, this is an eigenvalue problem where lambdas are nothing but eigenvalues of matrix A. So, again we write A x is equal to dx dt. Okay. So, x we write z e to the power lambda t. So, it becomes A z e to the power lambda t, and dx dt we write as lambda z e to the power lambda t. So, A z is equal to lambda z. So, that is what we get. So, what is this z? So, z is nothing but eigenvectors of A. So, if we now see that what we have assumed, the form of the solution we have assumed as x is equal to z e to the power lambda t. By doing this algebraic manipulation, we have identified what these lambdas are. These lambdas are nothing but the eigenvalues of A, and what this z is, these z's are nothing but the eigenvectors of A. So, again, so we write it, lambda i's are the eigenvalues of A, the set of corresponding set of zeta z i's are nothing but the eigenvectors of A. Therefore, the solution form, whatever we are assuming, we identify these unknowns, lambdas are the eigenvalues of A, z's are the corresponding eigenvectors. So, therefore, the solution vector x t, the solution vector x t can be expressed as a linear combination of z i's, the eigenvectors, because we have already proved earlier that eigenvectors are always independent vectors. So, eigenvectors form a basis set vector. That is the reason the solution vector that will be belonging to the same space can be expressed as a linear combination of the eigenvectors. So, therefore, we will be able to write x as a function of time as summation I is equal to 1 to n C I some constant multiplier, which may be a function of t multiplied by z I. This is let us say equation number A. Now, in this case, since A is a real constant matrix, then z I are time independent, because they are the eigenvectors, they do not depend on the time, because the matrix itself is a constant matrix, time independent constant matrix. So, therefore, the eigenvectors will also be time independent. So, therefore, x in the equation A must okay. This is a solution vector. The solution vector must satisfy the original equation, must satisfy original governing equation, and what was that? That was dx dt should be is equal to a x. So, we dx dt. So, we write d dt of x, x is summation c I z I. So, it will be summation c I z I, this summation is over I, a times x, x is nothing but summation c I z I. So, therefore, since z is independent of time, so this will be nothing but summation d c I dt z I is equal to a summation c I z I. So, this will be just c I is a scalar multiplier. So, time may be time dependent. So, c I will be out. So, a z I. So, we have already seen that a z I is nothing but lambda z I. We have already seen in the few minutes back that a z I is nothing but lambda I z I. So, we substitute that here. So, what we will be getting is that d c I dt z I is minus summation c I lambda I z I is equal to 0. So, you can take the summation series out, I is equal to 1 to n d c I dt minus lambda I c I z I is equal to 0. Now, you remember z i's are the eigenvectors of the matrix A. That means, they always form a, they belong to a basis set. And what the basis set is? The basis set is set of independent vectors. So, therefore, in order to satisfy this equation, all the corresponding coefficients should be equal to 0. We have already proved this theorem earlier. So, therefore, to satisfy this equation, all the corresponding coefficient should be is equal to 0. So, d c I dt minus lambda I c I should be is equal to 0. So, what is the solution to this? The solution is very simple. So, c I as a function of t will be c I at time t is equal to 0, that is c I at time t equal to 0 initial condition e to the power lambda I t. And therefore, you can write down the complete solution x as a function of t is nothing but summation c I e to the power lambda I t times z I, where z I are the eigenvectors. At time t is equal to 0, we have x 0 that is known to us, this initial condition set is known to us, this is nothing but summation c I 0 z I. Okay. So, let us say this is equation number B. Okay. Now, let us consider that y I are the eigenvectors of A transpose. So, these are all talking about the eigenvectors of A. Now, let us say y I forms a set of eigenvectors of the matrix A transpose. Then what you do? You take inner product of equation B with respect to y 1 and let us see what we get. So, inner product of equation B with respect to y 1 will give you inner product of x naught y 1 should be is equal to C 1 naught, inner product of Z1 and Y1. So, C1 naught we can get as inner product of x naught Y1 divided by inner product of Z1 Y1. So, likewise you can generically you can write as Ci 0 is inner product of x naught y I 0 divided by z I y I. So, solution becomes the complete solution now becomes x t, the time dependent solution vector is nothing but summation I is equal to 1 to n C I naught e to the power lambda I t z I, where lambda i's are the eigenvalues of A known to us, z i's are the corresponding eigenvectors of A matrix, they are already known to us, and C I naught will be obtained from this. And if you look into the expression of C I naught, this is inner product of x naught and y I. So, x naught is known to us, that is the initial value matrix and initial value vector, and y I is the eigenvector of A transpose. So, since we know we have already found out the eigenvectors of A transpose. So, this is known to us. Z I are the eigenvectors of A, y I are the eigenvectors of A transpose. So, they are known to us. So, we can compute completely what C naught C I naught is, that will be put here, lambda is unknown, z I is known. So, one can get the complete solution matrix. Okay. That is how one can obtain the solution of set of ordinary differential equation in using eigenvalue eigenvector method. Next, I will take up an example to demonstrate this method. Again, I will be taking up a two-dimensional problem, so that this can be solved in the class here, but one can do the similar thing for a multivariable, multi-scaled problem, multi-dimensional problem using numerical techniques. So, dx1 dt is equal to minus x1 plus 2x2, dx2 dt is equal to x1 minus 2x2. Suppose these two are the corresponding the governing equation of a transient chemical engineering problem. So, we write these two equation into a compact matrix notation dx dt is equal to A x, where x is the solution vector x 1 x 2 and A is the coefficient matrix, that is minus 1 2 1 minus 2. Okay. Now, let us go step by step. Step 1 is evaluation of eigenvalues. Eigenvalues of A will be, I am not, we have already seen how to evaluate the eigenvalues. So, the eigenvalues are in this case is lambda 1 equal to 0 and lambda 2 is equal to minus 3. Now, we can evaluate the corresponding eigenvectors x 1, capital X 1 and capital X 2, which are basically eigenvectors of A. So, for I am not going to, we have already seen how to do that in detail in the earlier examples. I am just writing the solution. So, for lambda 1 is equal to 0, the corresponding eigenvector is 2 1 transpose, it is basically 2 1, and corresponding to lambda 2 is equal to minus 3, you will be getting z 2 is 1 minus 1 transpose. So, these are eigenvectors. of matrix A. Next we evaluate, that is step number 2. Next we evaluate in step 2 the eigenvalues, eigenvectors of A transpose. And the corresponding eigenvectors are for lambda 1 is equal to 0, the eigenvector is 1 1 transpose, and for lambda 1 for lambda 2 is equal to minus 3, y 2 is 1 minus 2 transpose. So, therefore, one can construct the solution vector as x t is summation of C I 0 e to the power lambda I t z I, where I goes from 1 to 2. So, once we get that, then next step is how to obtain the C I's. Now, in this particular problem, let us say the initial value matrix is given as x naught, 2 and 3. That means, at time t is equal to 0, x 1 is equal to 2, and at the time t is equal to 0, my x 2 was 3. So, initial value matrix is given by 2 and 3, then you will be in a position to compute C I naughts. So, these C I naughts, because now Z i's are all known, we have all determined, lambda is we have determined. So, next is C I naught. C I naught can be determined by inner product of initial value matrix 2, 2 and 3, inner product between x naught and y I, that is the eigenvector of A transpose, and divided by inner product between z I and y I. Z I is basically the eigenvector of A and eigenvector of A transpose. So, we can on now all these we have evaluated y 1 and y 2. So, we will be in a position to evaluate C 1 naught and C 2 naught. So, if you remember, just put the value. So, C 1 naught is nothing but inner product of x naught and y 1 divided by inner product of z 1 and y 1, and C 2 naught is nothing but the inner product of x naught and y 2 and divided by z 2 and y 2. So, we know the initial value matrix, we know the eigenvector initial value vector, we know the eigenvectors of A transpose, we know the eigenvectors of A. So, we will be in a position to compute C 1 and C 2. So, C 1 turns out to be 2 3 1 1. So, basically you can write it as x naught t y 1 z 1 t multiplied by y 1. This will be x naught t y 2 z 2 t y 2. So, C naught C 1 naught can be written as 2 3 1 1. This will be 2 1 1 1. So, if you compute this thing, this will be 2 into 1 plus 3 into 1. So, this will be 2 into 1 plus 1 into 1. So, this becomes 5 by 3, and C 2 naught will be simply 2 3 1 minus 2 divided by 1 minus 1 1 minus 2. So, this becomes 2 minus 6 divided by 1 plus 2. So, this will be minus 4 by 3. So, once we have computed C 1 naught and C 2 naught, then we will be able to construct the complete solution, and in the next class we will be looking into the complete solution and finish up this problem, and that will give you a clear cut demonstration of how eigenvalue eigenvector method can be utilized in order to solve the homogeneous ordinary differential equation, set of ordinary differential equation by using this particular method quite elegantly. And we also in the next class we will be looking into what is the solution of set of non-homogeneous ordinary differential equation by using the eigenvalue eigenvector method. So, I stop this class at this point and continue the next class from this point onwards. Thank you very much for your kind attention.